Today we are going to, this is our agenda for this session. We are going to talk about the goals and the challenges of building the 2D engine. Yaron will then talk about the basic of WebGL engine to draw markers and basics for GIS in general, data on the web. Then I will talk about how we fetch data from feature layers in efficient manners in the JavaScript API. Then we'll move on to how do we use web workers to make the heavy processing, move the heavy processing off the main thread. And then we'll finish by some GPU goodies to talk about how we use the GPU to build data visualization. So goals and challenges, right? So with the JavaScript API, we have a few goals that we have set ourselves. First one would be visualizing more data in the web browser. So web browsers, they are much more modern than like 10 years ago. We can push more the limit of how much we can display and how fast we can display that data. The 2D engine, we really want to have also an immediate feedback, especially, for example, the map viewer, or if the map viewer, when you configure your layer, you will change very fast the renderer, or we enable, disable labeling, and so on. So we want to have a very good experience on this feedback. And we call that internally, it's called fast updates when we can. Then we want, of course, to have a good map navigation experience. So try to let the user zoom and pan and don't see any stutter or like the browser slow down, yeah, when the user pans. We want to innovate also in the visualization space. So recently we introduced the clustering in 4X. If you haven't tried it, you should, because it's really, really fast. And then, and it clusters a lot of data on the fly. But also before that, we had dot density, and we want to explore more in the future, like effects and so on. So that's one of the goals. But also we want to do more. Finally, we want to do more with the data that we have downloaded. So we download lots of features on the client, and we don't want them just to be there for display purpose, but also being able to query for them, being able to perform analysis, display data on charts, and so on. The challenges of all of this is that there is no rendering engine available out of the box in web browser. Otherwise, we won't be here to talk about it. We won't have any job. So our goal is actually to build a rendering engine that is tailored for our goals. The second challenge is, so more on the technical side, is, oh well, the first one too, but JavaScript is single-threaded. And so if we process ton of data, it might freeze the web browser because we will be using all the CPU. And there won't be any time left for the browser to let, for example, the user navigate and so on. And finally, the data sets that we are dealing with, they may be extremely large, either in the number of features that we are downloading or in the complexity of geometries. You can imagine the coastlines of countries. There is no limit to the precision or how detailed those geometries can be. They can represent many, many megabytes of data. So how do we deal with these very large geometries or very large number of features? So on the technical choice that we have made, we have used WebGL that we started quite some time ago, introducing into the JavaScript API. First, we used it to render vector tiles, and Yaron worked on that. And then after, we moved to render feature layer. Previously to that, we were using SVG. SVG has a lot of issues we will talk a little bit after about. But yeah, we worked on a WebGL feature layer. We introduced the first opt-in in 4.6 of the JavaScript API, and then we progressively enhanced until we were on feature complete on the feature layer rendering. And so in 4.10, the WebGL option was the only one available. Then after, we also managed to render all the layers into a single WebGL context. So all the tile layers and so on, everything is rendering in WebGL today. We build an efficient client and server communication. We worked closely with the server team and the hosted feature layer team to get the best communication possible between us, the JavaScript API, and the server. And it's a continuous improvement. There will be more improvement coming for sure in the future and so on. And then we decided to bet on using web workers to offload the feature handling of the main thread. So we are using web workers to do everything that the feature layer needs to do prior to display the features. So fetching them, processing them, and so on. We'll talk a little bit about that later on. And now, yeah, Yaron, it's for you.
All right, talk a little bit about the basics of WebGL and GIS. Okay, so WebGL is yet another graphical API. It is available to use through a browser. It is very, very fast in rendering triangles. And triangles are unfortunately not your GIS features. It is fast because it can communicate and dispatch commands over to the graphics card that is available, if it is available, of course. But it has some drawbacks. It is a big state machine and it does not like state changes, meaning that if you bind resources or change, things like blending off and on, it's just not, just doesn't like really doing that very often.
Like rendering, for example, a polygon, then a point.
Exactly.
It doesn't like changing all of this.
It does not like change it, yes. So what it means for us is that your GIS feature has to be triangulated, meaning that we take the polygon or polyline or markers and we generate triangles out of it, what we call mesh, and a mesh really is a soup of triangles. And then at render time, we reconstruct the GIS geometries from those rectangles. Yeah, you can see here on the right, a schema that Dario from the team put together that shows how we triangulate a line. WebGL is also using what's called a retained drawing mode. A retained drawing mode meaning that the library, in this case WebGL, is holding onto the drawing primitives, meaning that once we upload it over to the GPU, WebGL is holding it, and then drawing it the second time means that we let the library iterate over the primitives and render it, and that is very, very fast. This is in opposed to how SVG, for instance, does that, or even the canvas, where the user has to hold on to the geometries, and every frame needs to iterate over each geometry and rendering one by one what's called immediate drawing mode. I can switch over to the next one.
And the SVG also is pretty slow because it's a document, and we have no control about like when the web browser will decide to re-render that vector data that is in the SVG onto the screen. So it's also very slow compared to WebGL.
So a little bit on how WebGL is built. WebGL is built as a pipeline. What it really means, it means like, the schema that you're seeing here, there's like different stages, and the idea is that the output of each stage is becoming the input for the next one. You can see here that we push in the vertices in the form of what's called buffers usually, or textures. And then it goes to the vertex shader. The output of a vector shader is the primitive assembly or primitive generation. Then it goes to the rasterizer stage, eventually to the fragment where we're allocating colors to each fragment or pixel. And then, there's eventually the processing of the blending and other what's called per pixel operation, and then eventually gets rendered over to the screen. For developers, WebGL open up two stages which are programmable, which are the vertex and the fragment shaders. In the vertex shader, we transform the vertices onto the screen. In the fragment shader, we allocate the color to each of the fragments or the pixels. Traditionally, there's three main data types that WebGL can handle, which are buffers, when we use them to generate meshes, again, a soup of triangles. Textures, which we use for materials, think about raster data or all sorts of picture markers and such. And then there's uniforms. We're going to touch upon uniforms later on. Uniforms are basically constants that, when throughout the drawing, of a given set of primitives. So meaning that the value that are encoded in the uniforms can be accessed, from both the vertex and the fragment shader for the duration of the draw command. So, of course, we render GIS data with WebGL. And, here we're going to talk a little bit about drawing markers. The way we're drawing markers, of course, we have to translate the vertices or the geometries, first from world to device. Usually it's involved, using some form of transformation matrix. We have to translate them from the world over to the device coordinates. Then we bring each vertex to the right position and we generate what's called a quad. A quad is really nothing more than two triangles that sharing the single edge. You can see here, we brought, the position over, then we offset each vertex to the right position and then click another time. And then we end up having the quad. You see that there's the square in this case. And then after that comes the fragment shader, and then this is where we color the vertices. Now keep that in mind that we encode each feature such that it has enough information to render itself. What it does mean, it means that it's really not just the position that we have to encode. There's some more information that has to go in there to indicate what is the offset or the colors and things like that are really needed in order to draw the GIS data. Can you carry on? On the fragment shader side, this is where we decide which pixels to color and how to color them. In this particular case, we're drawing a marker, which is a circle. It has a size of 30 pixels, so half of that size would be 15 pixels. And you can see here that we consider the radius, of course, 15 pixels, which is 0.5 of the original size. And if you look at the fragment shader, click once more, as long as we are in a distance under 0.45 of the size, meaning less than 15 pixels, the color is going to be bluish. Once we reach the end, we start mixing it with white. And of course, once we go beyond that, then it's going to become transparent. And this is what generates that circular marker in this particular case. This brings us to the first sample of the simple marker layer. You can see here, Jan, you can zoom and pan. We fetch all the features over to the client, and then we process what's called the mesh. You carry on, zoom, and let's see what's going to happen.
Oh,
ooh, it's wiggling.
It moves.
All right.
Okay, so it looks like it's almost like snapping to some grid here.
Yes.
What's going on?
This is where WebGL is a bit of a challenge because WebGL is really holding on to 32-bit precision. Let's have a look at the sample first. If you go to the code of that sample. So we start by this is, we generate a simple map. We'll create an ArcGIS map. We set the base map to our vector tile. We create the map view. And then notice this is a custom layer and a custom layer view that we add. The implementation you just saw is a custom layer view. Let's look at generating the mesh. This is where we're iterating over the individual features. And then for each feature, it's called a little bit, we're creating the mesh. Notice that each vertex has, the position and then at the offset that you've seen that we're looking at the vertex shader implementation. And then if you scroll, we'll go back to the draw method a little further up.
Okay, sorry.
This is, no, this is here, this is where we bind the shader program. Then we bind the buffer data, and then we set the transformation matrix from world to device. And then eventually we dispatch the drawing command for all the vertices for all the features.
So in this command, all the points are drawn?
All the points are drawn in a single command. That's quite important. So now let's talk about the wiggly markers. Again, zoom in, zoom out, you can see that. And then let's talk about this a little bit more. So WebGL is using 32 bits and it is therefore limited to that precision.
Compared to JavaScript, which is 64
bits. So then think about when you zoom in quite a bit. As we discussed before, to render the markers, we have to apply a transformation. think about when you zoom in. So we have to bring those markers from far away to where we're at, where the view is. And so the translation is quite big. If you consider Web Mercator that has, let's say, a span of 40 million meters, and the 32-bit floating point, the number part has a precision of 23 bits. That gives about 8 million something. That simply isn't enough to sustain the precision that we need. And because of that, the items are wiggling. So how do we mitigate that? So there's really two primary ways of doing it. One is to use a local origin, meaning shifting the coordinate system origin to a place near the data, and then use relative coordinates. The other approach that we've taken is to use tiles. In a way, it's sort of the same thing because each tile has its own local origin. And then this is how we end up rendering the data. So tiles gives us way more advantages than just using the local regions. First of all, let's start with the precision problem. Each tile has its own local origin, which is the top left corner. So every time we render, we compute the transformation for that position. And then within the tile, the items are encoded relative to that position. So with that, we can maintain our precision and render the entire world using tiles. Actually, even more than that, because we use the tile local origin, the information that we encode in the tile, we can actually use shorts, which saves us memory on the GPU side, easier to handle and much simple for us to use. Tiles give us a lot more benefits than just dealing with the precision. When we're rendering with tiles, we use a part of two tiling schema, so navigating through the tiling tree is quite simple. Finding placeholder tiles is very simple. Even more, it gives us a means of a level of detail representation for our JS data as we zoom in and out, and Jan is going to talk about it a little bit more, very soon. But that goes even further because then we can only fetch the data we need to render, and we can only fit the data in memory that we really need. All right. Oh, I forgot wraparound. Yes. Wraparound becomes trivial when we use tiles because all you need to do is compute a very simple mod function so you know exactly which data need to be rendered when you pan east or west.
Yes. And that's compared also to the old ways of when using SVG, the 3x implementation of the SVG rendering is the way it renders SVG is that for each ring in each polygon, it figures out, oh, okay, so on which world is it? Like world 0, world 1, world 2, and so on. And how many worlds actually can it be displayed? Because like a polygon can start, when you have the wraparound, you can see each side of the dateline. You may see a part of the world on the left and a part of the world on the right. So you may have polygons that needs to be drawn twice or multiple times. So it needs to figure out this. Then after, for each repetition, it needs to draw and update the SVG document. So it's a lot of work. Whereas with tiles, we just have to repeat the tile, and then it's WebGL. It's cheap for it. Because the data is already in the GPU and so on.
Can you open the tile layer? So that is eventually the same exact layer. Can you please zoom in on one of the markers and then see what happens? As you can see, we can zoom in as much as we want. The tiles are fixed to their geographical position. They're not going to budge.
Yes. Up to which zoom level could we go with without losing precision?
Oh, we could go quite a bit. I think we can go, if I remember correctly, 26 or 27 level details.
And this is where after JavaScript loses precision.
Exactly.
Like when we reach level 26, it's the panning experience here that will suffer from the JavaScript precision because we are so zoomed in that the translations doesn't work anymore in JavaScript. Cool, that was great.
Maybe you can go and show the code for that particular layer.
Yes.
So we can see here in the second layer, this is our render. It's, beginning very much like the sample we just showed before. But if you further scroll down, we can see that eventually we set a transformation which is shared, for all the tiles. But then we render each individual tiles.
So the transformation is basically expressing the extent.
The transformation is, basically is a two-step transformation. First of all, we need to bring the vertices to the right place, and then we need to deal with moving them, each one of them, to where it needs to be relative to the tile. So if you go to the render tile, we see we're iterating over the tiles that we need to render, and then for each tile, we bind its own data. We set the tile-specific coordinate transformation. Again, each tile has its own local origin in more than one way. And then we dispatch a drawing for that particular tile. Nice. So that is the technique we're using under the hood.
So this is the VAO. VAO is the big array of coordinates that we saw earlier, right?
Eventually it is, yes. Yeah. It is.
So it's one command to move this to
move the data for the entire tile.
Okay,
and bind it and then let it be available for WebGL.
Very nice. So let's move on to data access. Yaron talked a little bit about that already. We use tiles to render, but we also use tiles to fetch the data. The two are not really linked. But we use the same concept anyway also for fetching. So yes, so let's take a step back. There are two strategies that we have for fetching features from the feature service. The one we'll focus on is feature tile queries. So we divide the screen into tiles, and then the screen, the view that you are looking at, the extent you are looking at, we divide that into tiles, and then we issue queries for each one of these tiles. The advantage is that we fetch only the data that is required to display. Also, the big benefit of tiles for features is that it's highly cacheable. So here we have, on the right, we have this little schematic that explains that. We have the feature layer. It's your feature layer that you use as a developer. And then when the feature layer issue tile queries, those tiles, because they are always the same, no matter what is the screen size, there will be the same extent. So the queries themselves, they won't change from one user to the other or when you reload the application. So the browser cache can cache those queries. So when you reload the application, if the data hasn't changed, you won't download anything from the server. Then we have the CDN cache. So that means that because those queries, they are always the same across all the devices, across all the users, these tiles, they can be cached on the content delivery network to be available fast for a lot of people. And then if your item is not public, so the CDN is only if your data is public, then the server has a feature tile cache directly in the server where in case, so the server also keeps those tiles in memory there, or in its cache. And then finally, there is the server in case the query needs to be executed against the server. The advantage of the tiles, and we'll talk a little bit about it, is that the payload of a tile is very small because the geometries are generalized on the fly by the server. So we fetch the tile for the resolution or the scale of the view, right? We don't need to fetch highly detailed geometries because you are very zoomed out. When you are zoomed out, we don't, a building down on the ground, it doesn't need all the details because it's even not visible at this scale. Then we have the other strategy is the snapshot. So snapshot consists of querying for all the features in one query or multiple queries, like paginated queries, but we fetch them once and then we don't query again the server ever. So the benefit is that we have less queries. Of course, if you zoom in and out, or if you pan, we already have the features of the client. We don't issue more queries. It's not yet available in 4x. It is available in 3x. We will work on this for future release, and basically we will use one or the other strategy based on your service configuration or your service data. So if the data has a lot, if you have geometries that are very, very detailed, then we will use feature tile queries. If you have a small number of points, that are already very simple geometries, we'll do a snapshot. The numbers are, it's heuristic, so it's like 50,000 points. 50,000 points, it's fine, we'll do a snapshot. If it's like 200,000, we're gonna go feature tile queries. Okay, so let's take a look at how it looks. Jeremy showed that at the plenary, this demo. Also, sorry, there is a blog post called Scalable Hosted Feature Layers in ArcGIS Online that details, you will see the little image I showed before, but it goes into detail about like the different level of caches that is available. So here is a layer of the buildings of New York. It's around like 900,000 buildings. And you can see that every time the layer performs a query, there is the query extent that is displayed. So because of the amount of feature, there is, the processing is a bit on the slow side, but we keep improving on that part. But you can see the queries are flying. The idea here is that if the query exceeds the limits, so in a tile query there are too many features, then we subdivide that tile into 4 tiles. Like Yaron mentioned, it's a power of 2 tiling scheme. And so what's very interesting about this is that this layer has been is public, and we enable the CDN on the item page of that feature layer, and you can see that everything comes from CloudFront. It comes into HTTP2 protocol, and these are PBF, so they are binary, so that it's highly compressed, and so on.
And these are a lot of buildings.
That's a lot of buildings. So if we zoom in, we're gonna see that there will be more. Like you can see the detail of the buildings. They look like they don't look good. But then as we zoom in, we get more of the precision. Oh, of course, there is a max scale on this layer. So for those feature tiles, we only fetch the required field for rendering. That's an optimization in 4x. We analyze the layer configuration based on the renderer, the labeling, the elevation info in 3D. We fetch the fields that are only needed for this, because to display the layer, this is what we need. If the user clicks on a feature and we want to have a pop-up, there is a pop-up template defined on the feature layer, then the fields for the feature you clicked on are going to be fetched on demand. If you want to use client-side queries and you want to have access to fields that are not into the renderer, they are not in the labeling configurations, then you can ensure that field is downloaded with every feature by setting the feature layer.outFields. Every field that is defined in this array will be fetched alongside each feature. And then the other big optimization that we do is to generalize the geometries to reduce the size, the size of the geometries. And there are 2 ways in ArcGIS to do this on the REST API. The first one is the Douglas-Pucker algorithm. It's controlled if you set the max allowable offset on the query. It's a very fast generalization algorithm that is very effective at removing vertices. But the problem of this algorithm is that it creates slivers when you have, meaning like there are holes when you have two adjacent polygons, because the vertices that are removed in one geometry is not guaranteed to be the same, like two adjacent polygons, they share an edge, and then so it's a set of vertices, and the algorithm, when it runs per geometry, and it doesn't know that the adjacent polygon, which vertices have been removed. It just like removes based on only the geometry it's looking at. There is the other algorithm, which is quantization. So we quantize the coordinates, and I will go into details about this. And what is great about this algorithm is that it preserves the visual topology. So the two adjacent polygons, they still look, adjacent. And it's very high compressible by gzip. So when the server brings the data, it goes through the server compression, and it's really fast. So let's take a look at a demo that showcase the difference between generalization. So quantization is available in since 2014, so it's quite a while, 5 years ago. 5 years ago, on hosted feature services, and it became available later on.
What do we see here on the left?
Yes. So on the left here you have, so it's the contiguous USA, and we can see the counties, we can see the counties that are generalized. And you can see all these slivers, all these different holes between the counties. And on the right side, you see the same data, but quantized. And now, no holes. It looks perfect, right? So here I can control the generalization. So let's say we generalize. Here we generalize at a resolution of the map view. So meaning that every vertices that are less than a pixel away from the next one is going to be removed. If I increase that generalization, we can see that the problem gets worse, right? But on the quantization side, it still looks, of course it doesn't look good, but at least at this,
at least no slivers.
Yeah, no slivers. So at this resolution, the result would be fine. This is how we set the generalization so that it fits for the current map view. So if we go back to our level 5 generalization, and we will compare also what is the size of these vertices. Let's maybe reload just in case. Okay. So let's take a look also at the payload size. Query. Okay, so on the left side, we have generalized, and we have not so much vertices, like 25,000 to draw all the counties.
That's after generalization happened.
Just after the generalization happened. It's about like 85,000, like not generalized. And then on the right side, we have many more vertices. Of course, like holes. And look at this, like here. So it looks great. It's 63,000. So it's much more. So we can think it's less effective. But actually, when we look at the size of the payload, uncompressed, it's like 630K for the generalization and 611K for the quantization. So it's roughly the same size for many more vertices. It's actually less, but for many more vertices. And now if we look at the compressed size, we can see like the ratio, the rate of compression, it's much higher for this amount of data. So we get more vertices, more data to have a better visualization, but for a much smaller payload. So that's great.
And topologically, it's better.
Yeah, of course, it's correct. So let's take a look how it works. So we have this original geometry. It's a polygon. Notice that we have like vertices that are close together. So the first thing we have to do is to determine the grid. So the grid is defined by an extent and then a cell size. So concretely, when we use that quantization, we define the extent will be the tile extent, and then the cell size will be the resolution of the tile. So the resolution at basically the scale at which that tile will be visualized. Then the second step is to snap each point of the grid. So now the grid, like the local origin, the origin of the tile is 0, 0, it's the top left corner, and we snap, which means we round the coordinate, the x and y coordinate, to the nearest point on the grid. Integer. And so now, yes, those coordinates that were into world coordinates, Web Mercator coordinates, are now in integer relative to that 0, 0 origin. So notice that vertices here that are close together, they snap to the same point. And that's how the generalization really happens. We remove the duplicated vertices. So we only send one vertex for all the vertices that lands into a single point. If you have a building and you are really zoomed out, all the points of that building will collapse to a single pixel. So now the geometry will be sent as null because it's not a valid polygon anymore. Then instead of sending coordinates in absolute values, we send deltas. So we start at the 0, 0, and to draw the feature, we move 1 in x, 8 in y, and then we go all around like this, right? So instead of having a set of very random coordinates, now we have repeatable patterns. So you can see that this delta is the same as this one. And this is where JZip compression is very much more efficient because a lot of geometries now will be encoded with the same delta. Like I move 1 in x, 1 in y, or minus 1 in x, minus 1 in y, and so on. So all the geometries will be encoded the same way, and they will look alike, and JZip can really compress this very, very well. So in terms of the API, the way you use it, if you want to use it, is to define your extent for the quantization, basically, reference, and then you have the tolerance, and the tolerance is basically, in this case, I want to display that tile in 512 pixels, so it's the number of map unit divided by the number of...
define the grid.
Yes, to define the grid. And then, otherwise you could use the view resolution, for example. So you may want to use this technique if you don't really care about having precise geometries, but you want to have some of it. You can pass the quantization parameters. But max allowable offset for generalization for a single geometry works good as well. And then you query for the feature set, and then you call unquantize, and it will unquantize the coordinates to get coordinates back into Web Mercator, for example. So quantization is available since 2014 in ArcGIS.com, in Enterprise 10.6.1. There are limitations for the generalization. The geometries that come back on the client, they are not the original geometries. So if you use client-side queries or use those geometries on the client to compute an area or to make sure that a point is contained into a polygon, you may get inaccurate result, right? So we have to be aware of that if making if you have relationships between geometries that are important, you can't rely on the generalization. And we introduced also last year the protocol buffers, 2 years ago. So basically, instead of sending back JSON, we encode the feature set into a PBF. It's a mechanism to serialize data into a binary format. It's developed by Google. It's an extra layer of compression. So on this data that you have seen from New York, it's around 20% better compression on top of the already pretty good compression of JZip. And it's available in ArcGIS Enterprise starting at 10.8, so in hosted feature services. So let's take a look at the demo. So it's the same demo as before. It's just like now we are asking for the server to quantize per tiles. Oops. So instead of fetching all the data up front, every time you pan and zoom, you can see the query going on and asking the quantization parameters. Oops. Yeah, this is what I want to show. so the quantization parameters for the tile query. And then if we look at the response, let's make that bigger. The features, the geometry. Okay, so in this case there are only points, so you won't see the deltas. I forgot, but they are like still numbers that are much smaller than the Web Mercator original coordinates. Okay, so now let's talk about offloading the work of the main thread. So we use web workers. Web workers, they are lightweight threads in the web browser. You can, from the main thread, you can start a web worker and then communicate with it. Right? It's very good to perform heavy tasks that are heavy on the CPU without impacting the main thread. So we can dispatch some work to the worker and then let it work, and then it brings us back the result. And then during that time, the user can pan and zoom and don't see any stutter. The problem is that the web workers, they don't have access to the memory in the main thread. It's not completely true, but like stuff like loaded modules, all your JavaScript modules that are loaded in the main thread, you need to reload them again in the web worker. And you need to transfer data back and forth between the main thread and the web worker. So I've built a set of simple worker demos so that to give you a little hint about how this works. So we have this demo where it communicates and just sends a hello world from worker. So let's take a look at this demo. So let me close this. Oh. Source. Yes, this is what I want to show. Okay, so we have, so when you build a worker, you need to have a script. And so that script, this is what is going to be loaded in the worker. So the script starts with a self on message. So we install an event listener on that message that will be called every time the worker receives something from the main thread. So in this case, what I do is that I take the data from the message event. I get, so I send two parameters from the main thread, the operation and the parameters. I check, do you want to call the operation called hello? Yes. So let's call hello with the parameters. And then we call that function, get the response, and send the response back. So now the function is this, return hello with the name from the worker. To create a worker, you have different ways, but the one I suggest is to use object URL just because of cross-origin, right? So if you try to load a worker with a URL that points to a cross-origin resource, the worker will fail, and it's kind of annoying, of course. So we avoid that by using create object URL. We pass the script that you just seen as a blob, and then we start up the worker. There is a cost. You can see it's synchronous. There is a cost in starting a worker, so you shouldn't spawn like too many workers because you're gonna freeze your UI. But in the meantime, once we have our worker, we set up the on message exactly like this one. So this on message will receive the post message back from the worker, and then we execute our hello function by posting a message, and we pass the data of that message, the operation, and the parameters. Now let's. It's, as you can see, it's not really user-friendly, because we kind of need to keep track of the message going and going to the worker, and how do we use promises, for example, to be able to make that nicer. So it's the same sample. It just like shows hello from worker, but in this case, I've wrapped my worker into a nicer API. My constructor, I start my script, same, and then I keep track of message ID. So when I will send that message to the web worker, I will pass that message ID, and then when the worker replies, he will send me back the message ID. So I know if I send multiple tasks to the worker, I know which one is done first. And so my class will has an invoke function where I pass the operation and parameter, and then I create a new message ID, and I return a promise. That promise will keep track of the message ID and the resolve and reject callbacks, and then we'll send that to the worker. The worker then receives that message, and oh yeah. So he receives the operations and then call hello and then sends back the message with the message ID. So now when we receive the message back, we know which message ID, which promise corresponds to that message ID, and then we resolve with the response. Of course, if we want to be complete here, we would reject if there was an error and so on. And the way to use that is that I create my new worker, and then I call invoke with hello and word, and then when I get back my response, I console log it. That's pretty cool. Now, like I said, we don't have access to the modules that are loaded in the worker. And for us in the JavaScript API, we wanted to be able to use Esri request, to be able to use the geometries, to be able to use all the goodies from the API from the worker. So what we did is to actually load an AMD loader, which is the Dojo loader, inside the worker, and then after tell it, okay, worker, like load this module that we have developed. So like that, it's very cool because we can share the code that we develop across the web worker and the main thread. So I've developed here a basic version. Let's go over it. So same, I start, you've seen the message ID and so on. What I do now is that I have my invoke, my receive, and so the operation I'm going to invoke is called load module, and I will say this is my base URL, and I want to load a worker file. The worker file is a very it's a very simple AMD worker file. It's just like log a message. So the load module, let's take a look at our worker script. So now I made parameters so that based on the operations, I will call either like hello or load module. So let's say I receive load module with the base URL and the module ID. I log that I want to load the module with the module ID. And then I use require.js in the web worker. And require.js I imported using import script. And so this will just add require.js in my web worker. So now I configure the web worker with the base URL, and then I will just require the module ID that I just asked and say, okay, the module is loaded, and this is done. So this is like a very slimmed down version of what we do, but you get the idea that we load a worker and inside we load the Dojo loader. This is not going to stay this way. We are moving the worker framework to use built modules. So for example, if we need to use Webpack and so on, we can't use require.js. So we have like different strategies of loading modules based on how you build your app. I mean, this is what we are working on. Okay. So all of this is great, but in the API we have exposed publicly the Esri core workers. It's the worker API framework. It's built to share a fixed number of workers for all the layers. So every time you need a worker and you use the worker framework, you get a worker from the pool of workers. We allocate as many workers as you have CPUs on cores on your machine. And then the work is distributed across all these workers for vector tiles. So every time we need a vector tile, display a vector tile, we pick one of the workers and then send that tile, that job, basically to one of the worker. Or in the case of a feature layer, we assign a dedicated worker for that layer. So feature layer view starts a worker, get from the pool of worker, but will always execute the functions on the single worker. So you can load any API modules, AMD modules in the worker framework, and you can also configure using Esri config. You can configure the worker framework to use your own modules in the workers.
So it means that developers can use the workers framework themselves.
Yes. Esri, if you use Esri request in the web worker, we install the mechanism to send back that request to the main thread. The main thread Esri request, execute the request. So like that, it has all the security information, the current tokens, and so on. Get back the result, transfer it back to the worker. So it's done all transparently, which is nice. We can't directly, if we wanted to use directly, make the I/O basically from the worker, we would have had to all the time transfer the information about current security and so on. It's much more complicated. So in 2D, we use this framework to do all the feature fetching, all the storage of those features, execute all the client-side queries. You can execute very complex client-side queries, and it will run just fine on in your web browser. And then processing all those features, those GIS features, for creating the WebGL data structure that Yaron was talking about. So let's run a quick demo about the worker framework. We can see that we load the Dojo Lite, which is a build of Dojo just for the worker, inside the worker. And then I have this worker that I built called calculator. This calculator just adds two numbers. It's very basic. Example that we use, it's our hello world of the workers. So the way it works is like you import, you require the Esri config, and you require Esri core workers. You can configure your loader configuration. So this will be the AMD configuration that will be used by the AMD loader inside the worker. You can also define the loader URL if you want to use a completely different worker. Dojo loader. So you pass the path. So I'm going to say that the modules that are in the worker folder will be at this location. And this is how it works. After you call open with the module ID that you want to query for, to open in the worker, you get back a connection, and that connection will have the reference to the loaded script, the loaded module inside the web worker. And then after you can call invoke like I just showed you with add, and then we pass two numbers and the worker just like give us the answer. There are some other options available for you. I have put the link in the slides, sorry. So Comlink and Greenlet, they are like nice, I would say, wrapper around worker API that is pretty rough. It's a different take on what we are doing. It's the same. And then there is a Webpack plugin that is very convenient to use in Webpack, but then it's a plugin, it's a loader. So that means that if someday you need to, Webpack is not trendy anymore, then you will have a hard time to remove this kind of dependencies. Kind of like the Dojo AMD plugins. Okay, so we modified the worker examples from the example from earlier. Let's take a look. Is it here somewhere? Oh no. Yeah. So now, like, what is great about this is that as you pan and zoom around, it's like super fluid. Like you can see like the tiles are coming in. If the workers aren't there available, then you would see definitely the problem.
Notice that the UI is running freely, no stuttering, no nothing.
No nothing. Yeah. All right. So let's. Yeah.
All right, let's talk a little bit about GPU-based visualization. That's really the secret sauce for our API. So remember, I mentioned that the main data structures that will fit into WebGL are buffers, textures, and uniforms. Buffers and textures, are great. You can fit a lot of data onto them. So this is where we add the information, the vertices, the positions, attribute data, and so on. They're great. The thing, though, it takes time to process them, whether to upload them to the GPU or the data, modify the data inside this data structures. Here on the right, you can see an example that we had multiple markers together. You see the positions, and you can see what we call VV1, VV2, and so on. This is what we refer to as visual variables. In this case, it will be the positions and the angles, not positions, colors, positions, and so on. These are really attributes that we would later on use. And then there is the uniforms. Uniform is another data structure that you can fit WebGL. As I mentioned before, it is really a constant for the invocation of a draw command. They can fit a lot less data, but they're very, very, very fast to modify. You can modify uniforms even in between draw calls. Here on the right, on the bottom right, you can see how we update the uniforms. In this case, it would be the minimum, maximum size values and the actual size of the markers that we would eventually need to render. And then after that, you see how we push this uniform to WebGL. Now, another thing, and we're going to talk about this a little bit later, there is a great deal of importance on how we organize the data in WebGL, so we can issue the very few commands, and then we take out that. We take advantage of that. Again, also remember what I said before, that each feature that we encode, we don't just encode the position, we encode information that is sufficient for that feature to render itself on WebGL. This is also critical for how we do things in the API. We'll start with the data for the data-driven. And again, this is an evolution of the set of samples that we've been showing throughout this demo. Let it load. It can take a second or so. All right. So you can see, oh, you reloaded it. All right. Okay, so you can see maybe you can even change the color scheme just for the fun. So you can see this is where we have the same features, it's the same data, but you see that each feature has a different value, so a different color and different size. If you maybe go into the code for that sample, you can see that the drawing is pretty much the same. If you go scroll up, so this is the render command for the layer. If you scroll now further down, and further, please. So we can see here we're setting the matrix for the old the data, and then we push some uniforms, and then we render each tile. Go to the render tile method.
So these are the two uniforms.
Yes,
okay.
I didn't want to go through this, but you see that rendering the individual tiles it looks exactly the same like before. So how do we do that? So of course the key was to set the uniforms that set the ranges, and then there's some work that we do on the shader side. Now go back to the slides.
Oop.
And then switch over to the next one. Yeah, okay. So, as I said, we do most of the work on the shader side. We encode the information, the attribute data that we use to drive the size, the color, and so on with the data of that feature. And then when we execute the draw, the shader code take that value for those vertices for that feature. And then what it does, it compute the values on the fly, giving the ranges that we pushed through uniforms. Those ranges would be the minimum, maximum attribute value, and maybe the size. And then all that is left to do for the shader to do is do a very simple linear interpolation to compute the values on the fly. In this particular case, you see how it is computing the width for each marker. And then from there on, it's the same process. You see, we multiply by the transformation matrix for that tile and so on, and then we offset the vertices to the right position. And of course, the offset corresponds to the size that is computed before. This is super, super, super fast. And then this is really how we control other visualization aspects, such as the colors, size, angles, and so on and so forth.
So Yaron, you just said that it's a very simple linear interpolation between the min and max size, the min and max value of the field and the min and max size. But the thing is, it's very fast and it's very simple. But then in the case of SVG or Canvas, you would have to do that in JavaScript for every single feature. So it is fast for the GPU, and this is the benefit of building our own WebGL engine.
Exactly.
Is that we can say, we can draw the features in a very specific way, so that we can take advantage for the size visual variable and so on.
And even more, remember, I said that setting uniforms is very fast.
It's very fast.
So if I modify now the range of the value for the uniforms, all of a sudden we can get a very, very nice, very fluid visualization. This is, by the way, the CPU side of that same code. You can see here that we've been setting the transformation matrix and other things, but we can also we're also setting the range, whether it's the color ramp or the minimum, maximum size values that we then evaluate on the shader side. Again, we use that to control color ramps, sizes, opacities, and other aspects of the visualization that we do with the API. So, switch over. Now, that brings us to some more things. Again, remember I said at the very beginning that WebGL is a state machine. It doesn't like, we'll get there in a second. It doesn't really like state changes. So, and not only that, relatively, of course, JavaScript is slow. So that, let's say we had 10,000 markers and we had to issue a drawing command for each individual marker. So we end up with way more than just 10,000 JavaScript draw codes to dispatch the rendering. So the key is to combine all the data onto a single data structure that we can dispatch only once, at least per tile. So, and then what we need for that, we need to organize the data in a way that is adjacent in memory. Of course, use the same shader, potentially bind to the same textures. And once we maintain or keep this criteria, we can combine all this to a single draw instructions. So we generate very, very few, or relatively very few JavaScript instructions to draw this data. And this is, again, critical for the way that the JavaScript is rendering. Let's go to the sample. So again, that is the same sample, and we can see how we are applying the fast updates. Again, it looks the same, but notice that as Jan is changing the color ramp, it changes on the fly. There's no hiccups. Use the slider to also modify the size.
Yes.
And you can see as he dragged the slider, the size changed on the fly. And how we do this? Simply by setting the uniform values. There's really nothing more than that. And then the shader does the rest of the work for you.
So it's basically one line of JavaScript.
It's a single line of JavaScript.
To update the size for all of the
For all the markers, yes, in this particular case. And that what makes it really, really, really fast.
So it's one line, but at the same time, all the work has been done in the batching.
Yes,
right.
exactly.
So all the engineering is there. Like, how do we organize the data structure?
The key work is to figure out how to organize the data in a smart way. And of course, there's also some trade-offs, because the more data you add, you would add more memory. And then if you add very few data, that you would end up with a lot of draw calls. So there's really a balance between, there's a lot of thinking and a lot of engineering in figure out how to set this data in a clever way that would allow us to visualize it fast, fetch it in a fast way, and then apply updates and so on. And of course, this is really the tip of the iceberg, because there's so much more that goes in the API.
Yes, it's just one thing. So what about the other geometry types, for example, like drawing polygons? So drawing polygons and polylines is much more complicated than markers. Triangles, they need to be valid also. They need to have some size. There is like a lot of quirks and bugs and that we went through. I think we are in a good place right now. We expose, if you want to build like custom visualization, like we exposed a bunch of triangulation utilities to triangulate lines and polygons and markers. So let's take a look at a little bit at it. So we have this sample from 414 that shows how to draw these polygons with holes, this line here, and these markers, right? And Dario spent a lot of time also documenting and explaining how it's supposed to work.
Show the graphics. It's so nice. The slides.
Oh yeah. So he explains like the different parameters for you to control the triangulation of polylines. Triangulation or tessellation? I always forget.
It's triangulation of lines and tessellation of polygons.
Okay. And so yeah, so the shading for this and yeah, the different possibilities. So why would you use this? It's really like if you want to, we tailor the feature layer view capabilities based on what we want the platform to be. But then sometimes you may want to have, less capabilities, but really, really fast. And you may want to use custom layer views, custom layers to really like build this kind of experience.
Actually, tomorrow, Dario and myself record another presentation that talks exactly about generating building custom layer and layer views in the JavaScript API.
But for
so
you,
tune in.
Yes, but for you, it's going to be available right away on on YouTube or something. So it's called ArcGIS API for JavaScript, building custom visualization using WebGL into the map views. I've seen the samples and it's amazing. So be sure to check it out. And for us, we are done. Just to plug this back again up. Oh, I lost my PowerPoint. It's fine. Let's all the samples, all the code that you have seen is available on GitHub, and so you will have access to the different stages of the presentation of that custom feature layer. So if you want to dig into the code of building a custom visualization or feature layer for markers, there is plenty to look at. There are the examples about the quantization, the tile drilling, the web workers. And with that, we are done.
Thank you.
Right. Thank you, Yaron.